the material that is going to cover, we're going to cover this week is going to be part of the exam. So today, Wednesday lecture, both of them, the material we cover here is going to be part of the exam, of the second exam. Okay, on Monday, I will prepare a review as we did last time. So I'm going to basically answer questions about, you're going to have an extra homework that's going to be due on Monday. I'm going to answer questions about that homework, and also I'm going to show you a outline of the topic you should be ready for the exam. Also, you're going to prepare a formula sheet, a new formula sheet for this exam. So make sure you start working on that. Basically, put the formulas that we have been using in the past for the materials that we started covering after the first exam. So you had a question?
What chapter did we talk about?
We covered part of chapter 3. So there's a couple of sections from chapter 3 that we didn't include in the exam. Chapter 4 and chapter 5. And we're going to cover part of chapter 6 today. Okay? Yes, sir.
For the binomial hypergeometric first time, are you going to provide tables?
Yes, that's a good question. So there's some tabulated tables in the book that you can use to solve the problems in chapter 5, specifically for the binomial, the Poisson. So you don't have to use a calculator to find those probabilities. Once you state the problem, you can use a table to find the numbers. So I'm going to provide those tables as well. So you can use your calculator or you can use the table. Any other questions? Okay. So the new material is covering chapter 6 of your textbook. This is continuous probability distributions. But before we get to the new material, let me just provide a review of the discrete probability distributions that we covered, or that were covered in the video lecture. Okay? So we have five probability distributions that come from the discrete type. The first one is the binomial distribution. And this distribution basically, okay, before we discuss the distribution, this is what I want you to get from these materials. We have been discussing discrete and continuous distribution, how to compute the expectation, the variance, how to basically, if you want to find the cumulative distribution, how you integrate, how you look at the summation for the discrete case. Now, we are focusing on specific distributions which are very useful and commonly used in engineering. For the discrete cases, we have the binomial, we have the hypergeometric, the geometric, the negative binomial, and the Poisson. Those are the five that we're discussing in this course. Okay? Those are very important because, again, you can model a lot of real problems using those probability distributions. Okay? So, the important thing about this lecture, or the lecture we covered on the video, is that you need to be able to identify when are you going to use these distributions, because they do not apply to all cases. If I give you a problem, you should be able to identify the characteristics of the problem, and using those characteristics, know what distributions you should use. That will also apply to the continuous probability distribution. Okay? So, for this topic, we have the binomial. So, in the binomial, we have these three characteristics, basically. We know that the trials are independent. We know that each trial results in only two possible outcomes, a success or a failure. And we know that the probability of success in each trial is fixed and is given by P. Okay, so remains constant for all the experiments. And the random variable that we are trying to solve or to find the probability is the number of successes in n Bernoulli trials. So the type of question that you can answer basically is finding the probability that in the next 18 samples, exactly 2 are contaminated. So you have a number of trials, and you're trying to identify the probability of having exactly these numbers of successes. That's the type of problem you can solve with the binomial. Now, when you look at the hypergeometric, in this case you have a big N, which is essentially a sample from your population. That's what we call capital N. So we have a set of N objects, and from this set we have K of them that are classified as successes. Okay? Now, if you subtract N minus K, you know that you're going to have that number of failures. Now, for the first distribution, the binomial, we were assuming that we were sampling with replacement, meaning that we take a unit, we put it back, we take another unit, we put it back, and so on. For the hypergeometric, we have a sample, N, capital N, number, let's say 100, and from that set of 100 objects, we are taking a small sample. Let's say we take 20. From the 100, you take 20. That's what we call N. So we're taking 20 objects from 100, and that's our N. So we're going to base our probability from these small N objects. Okay, so we are sampling without replacement. We are taking this amount of objects, and we're going to compute a probability based on those objects, N objects. Okay, so the random variable X denote the number of successes in the sample, in this small N. Okay, so I want you to see that difference. On the first case, the binomial, you are replacing, you're taking one, replacing, taking another one, replacing. In this case, you take a sample and you base your probability from that sample. Okay, and for that case, we have the formula to compute the probability for the hypergeometric. The negative binomial. So this one is related to the binomial. Still have a probability that is fixed. The probability of failure is going to be the complement of that probability, which is 1 minus p. And the random variable that you're looking at is the number of trials on which k success occurs. So here you want to know how many trials do you need to achieve these many successes. Okay? That's the negative binomial. And again, if you can write down that on a paper, this distribution when you're looking for this distribution when you're looking for this, that will help you a lot. This is the type of questions that I can answer with this distribution and so on. So that's the negative binomial. The geometric is also similar, but for this case, instead of looking at the k number of successes, we are looking. It's a special case of the negative binomial in which that number of successes is 1. So you want to know how many trials until you get the first success. That's the negative binomial, the geometric, which is very similar to the negative binomial. And finally, the Poisson. And for the discrete case, this is the most important distribution. Okay, so the Poisson, this one you're going to be using and seeing that distribution a lot. So this probability, and the thing with this probability is that it has some nice properties. For example, the mean and the variance is the same, which is lambda. The other thing is it has the memoryless property, which means that it doesn't take into account whatever happens before this time interval, doesn't affect the actual probability. And we're going to talk about that later in this course. But again, this one is the most important. So in this distribution, the probability associated with the number of occurrences in a given period of time. And you can find that probability using this.
So it's just the time frame.
is basically saying I'm gonna have an hour, I'm gonna observe an hour, like the number of cars that are gonna cross this street for an hour. And this process can be modeled using the probability Poisson distribution. You can estimate the probability of how many cars are gonna cross the street if you have a mean and a time period. Okay, so this is a type of distribution that you're counting for a specific period of time. And this is used a lot if you want to model, for example, the number of arrivals in a bank, the number of customers arriving to your store, the number of parts or requests you're receiving in your warehouse. That type of process you can model easily with the Poisson distribution. Okay, so those are the five discrete probability distributions that we are covering in this course. And again, from those five, this one is the most important. The other thing you need to remember is if I ask you the probability of x equals something, you can find that probability by just substituting the number x in the formula. But what will happen with the continuous? Will you be able to solve a problem with x equals 2? No, right? And you remember why? You integrate for the same interval, that integration will be 0. So that doesn't apply for the continuous, but for the discrete case, it applies. Also, if you find the probability of, let's say, x being less than 3, what would you do for the discrete?
Zero, 1, 2.
Correct. You find the probability of 0, 1, 2, and you add those probabilities. For the continuous case, what do you do? You integrate from 0 to 3. Okay, so remember, that's something we discussed already in class, but you will be using that in these problems. Any questions? Okay, so that's for the discrete. Again, the homework, chapter 5 is basically using these 5 distributions. So if you are able to identify when you use each distribution, what type of problem you can use each distribution. And actually, if you look at the book, the problems are divided by section. So the first section are binomials, so you should be able to solve those problems with the binomial and so on. So the homework is basically subdivided by distribution. But be aware that each distribution is basically targeting a specific type of problem. Okay? So let's start with the new material. So again, now we're going to transition to the continuous probability distributions. And I have a list of distributions here. Basically, we have 7. But as you can see today, we're going to focus on these 2. From the continuous probability distribution, the most important one is this one, the normal. And the reason why is it has very unique properties. Basically the shape of the distribution is very useful to model different problems. Okay, so that's why this one is very important. Also, some of the statistics, measurements, and theorems, and other important things from statistics are based on some of the properties from the normal distribution. I don't know if you have heard about the central limit theorem, for example. The central limit theorem is based, or basically comes from the normal distribution. Okay, so let's get started. Again, as I did in the video, just want you to be sure on when we are in this class. So we started by covering these measures of locations and variability. Then we moved to the probability side. So we discussed what a sample is, the event. We learned how to count sample points. We talk about the probability of an event. Then we discuss random variables. We talk about probability distributions, discrete and continuous. And from there we talk about joint probability distributions. And now, before we get to that, we use this measures of locations, and apply them to random variables. Last week, we covered the specific probability distributions that come from the discrete family. And today, we're going to start covering some of the probability distributions that come from the continuous distribution family. Okay? So we're going to start with the uniform and the normal. So the learning objectives, again, understand the assumptions for some continuous probability distributions. What are the assumptions? When are you going to use them? That's the most important part, because if you know when to use them, then you are able to apply them and solve the problems. Select an appropriate continuous probability distribution to calculate the probabilities in specific applications. Calculate the probability and calculate the means and the variances. For this lecture, this is very important. You're going to learn about the standardized normal random variables, and you're going to see why is that very important. And we're going to use the table of the cumulative distribution function of a standard normal distribution to compute or calculate probability. Okay, so at the end of this lecture, you should be able or feel comfortable doing all this. So let's start with the uniform distribution. Okay, so the uniform distribution doesn't have a lot of applications, but it's very important because it gives you an introduction of how to use the continuous probability distribution. So it's one of the simplest continuous distribution in all of statistics is the continuous uniform distribution. Okay, and it is characterized by a density function that is flat, and thus the probability is uniform in a closed interval. So what you're going to have is just a flat line within two intervals, or within an interval from A to B. And again, the applications are limited, but serve as a good introduction to other continuous probability distributions. Yes, it's going to be constant, let's say, from 1 to 1. Good question. Any other question? It's limited, and I'm going to show you a figure on the next slide. Yeah, so you have a closed interval, so it's going to go from A to B. Those are the limits. So, the density function of the continuous uniform random variable on the interval AB is given by this expression. So basically, you're looking at 1 over the difference or the range of the interval. So B minus A. And that's going to be the value from within this interval and 0 elsewhere. The density function forms the rectangle with base B minus A and a constant height of 1 over B minus A. Okay, so you're going to have a rectangle like this one. So the uniform distribution is often called a rectangular distribution. So this is how the PDF looks like. So you're going to start with the limit 1 and limit 3. And you're going to have a flat or constant line within those points.
That's only works inside the uniform distribution. It's not really that form. It's not really the actual probability.
Well, the probability you're going to find it using the area under the curve, just like with all the continuous distributions. So the shape of the distribution for the uniform is this. If you want to find the probability for, let's say, less than 2, then you need to integrate from 1 to 2.
We sort of need 1 to 3.
1 to 3 is for this case,
right.
This is just an example. For this case, we have the distribution, a uniform distribution that goes from 1 to 3. So the shape is going to be this, but this can apply to any limits. Okay? Any other questions? Okay. So again, this is a PDF. Anyone remember what is a PDF? Correct. probability density function. If you want to get the cumulative distribution from a PDF, what is it? Anyone remember? You integrate, right? So you get the probability density function. If you want to find the cumulative, you integrate. Okay? So let's look at this example. So in this example, suppose that a large conference room at a certain company can be reserved for no more than 4 hours. Okay? But both long and short conferences occur quite often. In fact, it can be assumed that the length x of a conference has a uniform distribution on the interval 0, 4. So basically what we're saying here is that each meeting can take from 0 to 4 hours, and we can model the length of the meetings using a uniform distribution. So the question is, what is the probability density function for this problem? So coming from the definition of the PDF for a uniform, right here, so we're going to define for this problem the PDF. And the PDF of a uniform is given by 1 over b minus a. So in this case, what is the value of a? 0, correct. So a equals 0 and b equals 4. So the density function, let me write the formula here. So the density function for a uniform, so the problem is telling you that this follows a uniform distribution. So the PDF is f, you need to know a and b, and it's going to be equal to 1 over b minus a for x within a and b, and 0 elsewhere. Right? So part A, basically, if you want to find the PDF, this is going to be equal to 1 over b minus a, so it's 4 minus 0. And this is for x within 0 and 4, and 0 elsewhere. Questions? So we know how to, you know the PDF for a uniform distribution. That's given. So you're finding, you know that that process follows a uniform distribution. So for that case, you want to basically write down what is the uniform distribution for this problem. So you have the PDF. Now, part B. Part B is asking what is the probability that any given conference lasts at least 3 hours. So what is the probability that we are looking at? Say that again? At least 3 hours. 3 or more, right? So we are looking at the probability of x being greater or equal to 3. Right? So how do you find that probability? You have the PDF. What's that?
Integrate.
Correct. So you integrate from 3 to 4 because that's your upper limit for the distribution. 1 over 4 dx. Is that clear? So while you're integrating, you're finding the probability. To find the probability for a continuous distribution, you integrate. You have the PDF. You found the PDF. You know the limits. So you integrate the probability distribution from 3 to 4. And if you solve this, what will be the value? 0.25 or 1/4. So basically the integration is just 1/4 times x, and you evaluate that from 4 to 3. And this is 0.25. Any questions? So as I mentioned earlier, this is a very simple distribution, easy to manage. The PDF is very simple. If you want to compute the mean and standard deviation for the uniform, can you go to the next slide? Just wait a minute. You can find the expectation. You remember how to get the expected value of a continuous random variable? Anyone else remember? What do? So you have a continuous random variable, and you want to find the expectation or mu. So the expectation of x, which is equal to mu. For a continuous random variable, you do the integration of the function times x dx. So if you want to find the mean of a continuous distribution, guess what you do here? Just multiply this PDF by x and solve. That will give you the expectation. So just want to make things easier for you, so the mean and the variance for the uniform are here. But you can get to that result by integrating the PDF of the uniform and multiplying that function times x. So this is the mean and the variance. The mean is just a plus b divided by 2. The variance is b minus a squared divided by 12. So let's look to another example. This one is going to be more interesting for those in electrical engineering. So here we have uniform current. So let the continuous random variable x denote the current measured in a thin copper wire in milliamperes. Assume that the range of x is 0 to 20 MA, and assume that the probability density function of the random variable is given by this. F of x is equal to 0.05 for x from 0 to 20. Okay, so what is the probability that the measurement of current is between 5 and 10 milliamperes? So what do?
Integrate.
Correct. What is your function? F of x.
0.
Correct. So f of x is going to be 0.05 for x from 0 to 20, right? And 0 elsewhere. So if you want to solve, let's say this is A and this is part B. So to find the probability, you integrate from 5 to 10, 0.05 dx. And again, this is just 0.5 x evaluated from 5 to 10. And this is equal to 0.25. So that's the probability that the measurement is between 5 and 10, is 0.25. And if we draw this is 20. So basically you're looking for this area, 0, 5, 10, 15, and makes sense, right? It has to be 0.25 because it's just 1/4 of the area, right? So you're looking at the integration from 5 to 10. 5 to 10, you have this area for the distribution. You're basically dividing the area in 4. You're looking at this area, the probability has to be 1/4, 0.25. Okay? Let's solve part B. Compute the mean and the variance. So the mean, again, equals A plus B divided by 2. So in this case, A is 0, B is 20, divided by 2, this is 10. And again, if you look at the distribution, the mean, this is constant, so the mean has to be in the middle, halfway through, right? So 10. And the variance, 20 minus 0 squared divided by 12. So this is 33.33 MA squared. Okay, so, yes, sir. What?
Where did the 12?
12? Well, here, oh yes, it's the formula of the variance from here. Any other question? Okay, so I guess you're ready to work on a problem by yourself. So the only way I would know if you're understanding material is that you try it. So I'm not gonna collect this problem. Just I'm gonna give you 5 minutes to work on it. And please, if you don't understand what you're doing, raise your hand and ask questions. Okay? So practice 5 minutes to be very simple. Yes, sir. For the first part, this will give the mean and the, for the second part, yes, just find the, you need to find the PDF and also solve for less than 2 minutes. Raise your hand if you're done. Okay, one more minute. So the first part should be really easy, right? It's just using the mean and the variance formulas for the uniform. So A, we have mu. Remember, the mean is equal to the expectation. So this is equal to 1.5 plus 2.2 divided by 2. And this is 1.85 minutes. Questions? No question. Okay. So the variance of the random variable is just 2.2 minus 1.5 squared divided by 12, and this equals 0.0408 minutes squared. Questions? Okay. Guess the second part will be a little more difficult. So what would be the first thing you need to do to find the probability? Find the PDF. In this case, we know this is a uniform distribution, right? It's uniformly distributed. So the PDF, we know, equals 1 over b minus a. So in this case, this is 1 over 2.2 minus 1.5. And this is our PDF. And this is true for x between 1.5 and 2.2. So f of x equals 1 over 0.7 for x between 1.5 and 2.2 and 0 elsewhere. So this should be the best, this is the right format for the PDF. Okay, so the values, this PDF only applies for this page. So if you need to, now you need to find the probability that x is less than 2. So the probability of x less than 2, just have to integrate the PDF from
1.5 to 2.
Correct, 1.5 to 2. Questions? Yes, sir.
Yeah. Integrating this function seems a little dry. It's clearly a square, so why would this be rectangular?
Say that again?
All of these distributions are rectangular. So
Yeah.
why not just take the difference, which is width, so 2.2 minus 1.5, or 2 minus
You're
1.5,
finding the area, right?
multiply the width.
Yeah, and that's true for this thing, because it is a rectangle. But I want to keep the same format throughout the lecture, so everyone follow what we are doing. So for the continuous distributions, this will always apply. If you find the PDF, you integrate, you get the probability. Okay? That applies because this is a rectangle. So you're basically finding the area of the square. Okay? But I don't want you to get confused. So this is just the integrate from 1.5 to 2.2.
Yeah, just a two.
Oh, sorry. Yes, this is 2. Good. This means you're paying attention. So you go up to 2 because we are looking at the probability of x being less than 2 of 1 over 0.7 dx. And when you solve this, this is 0.7143. Questions? No questions. So again, the most important thing here is you need to find out how to get the PDF. So the uniform is 1 over b minus a. And then you solve for the probability you're looking at. Questions? So this is for the uniform. Now we're going to transition to the normal distribution. And again, as you will see in this slide, this is the most important continuous probability distribution in the entire field of statistics. That's the normal. Okay, so that's why we're spending a little bit more time on this one than in the other ones. Its graph is bell-shaped, as you can see in this figure, which is approximately describes many phenomena that occur in nature, industry, and in research. So that's why this is very important. You can describe many phenomena using the probability distribution, the normal probability distribution. For example, we can describe the physical measurements in areas such as meteorological experiments, rainfall studies, measurement of manufacturing parts, errors in scientific measurements. And right now, working with Dr. Tondandin in finding, using the normal distribution, finding ways of predicting the power for solar panels. So that's how powerful this probability distribution is. Okay, so you can basically model a lot of phenomena using this distribution. So a continuous random variable x having a bell-shaped distribution is called the normal random variable. And the mathematical equation for the probability distribution of the normal variable depends on the two parameters mu and sigma. So mu is the mean, sigma is the standard deviation. Oops, sorry. Okay, so this distribution will depend on these two parameters. And in order to find the mean, just look at the average, just the typical mean. The same thing for the variance. You can find it using this sample variance formula. Okay, so the PDF or density function of a normal random variable with mean mu and sigma squared is this. So can you imagine trying to integrate something like this for x? It will be kind of hard, right? And we have the value for p and also for the exponential. So just keep that in mind. If I ask you to solve the probability or find the probability using the normal, you're going to have to integrate this for x, and it will take you some time. It's not impossible, but it will take you some time. So before we get to a method for not going through that process and integrate the normal distribution, let's talk a little bit more about the properties of the normal. So again, once mu and sigma are specified, the normal curve is completely determined. So in this case, we have two normal distributions, same shape, but the only difference is that they have different means. So in this case, we have the same standard deviation, but different means, so that's why one is located in this side and the other one is located to the right. Um, the two curves are identical in form, but they are centered at different positions. Okay? So as you can see, you can have different means. You still have the same shape, but you're located on different places with the same standard deviation. Now, if you have the same mean, let's say we have the same mean, but different standard deviation, this is what happens. So with a larger standard deviation, you're going to have more variability, so your curve is going to spread more. So the two curves are going to be centered exactly at the same position, but the curve with the larger standard deviation will be lower and spread out farther. Did that make sense? Yeah, more both when you sum the area of the curve, you're gonna have the same probability, which is equal to 1. Okay? So that's why when you change the parameters for the standard deviation, for example, you're gonna have more variability, but you still have the same area. So that's why the curve is gonna spread more. Now, if you have both different standard deviation and different mu's, you see that you're going to have two different curves. One spreads more, the location of the means are different. So this is the case in which you have different means and different standard deviation. Okay? This gives you better understanding of the shape, and this is going to be useful later. Okay? So just make sure that you basically understand how the shape looks like and how the standard deviation and the mean affects the shape of the norm. Okay, so properties of the normal curve, the mode. Anyone remember what's the mode?
Most frequent.
Yes, we didn't discuss the mode in class, but it's the observation that repeats the mode in your sample. So that's the mode, which is the point on the horizontal axis where the curve is maximum, occurs when x equals mu, which is the mean. The curve is symmetric about the vertical axis through the mean. The normal curve approaches the horizontal axis asymptotically as we proceed in either direction away from the mean. And finally, the total area under the curve and above the horizontal axis is equal to 1. Okay? So that applies, the last one applies to all the probability, the continuous probabilities, and also to the discrete, actually to the continuous probability distribution. So the mean and variance for the normal are mu and sigma squared, and we know how to compute them. Okay? So in this lecture that we are discussing right now, for now we're going to assume that the two parameters are known. Okay, so I'm going to give you that information. And we're going to assume that we have that information from previous investigation. But later in this class, we're going to have, you have to make statistical inferences when mu and sigma squared, or the mean and the variance, are unknown and have to be estimated from the data. So for now, we're going to keep things simple. We're going to assume that we know the mean and the variance. But later in this class, we're going to assume that we don't know the data and we're going to have to compute the mean and the standard deviation. Okay? So the area under the normal curve. So again, why the area is important? What is this shaded area telling you? What is that? That's the probability. Okay? So the curve of any PDF is constructed so that the area under the curve, bounded by two coordinates, x1 and x2, x1 and x2, equals the probability that the random variable x assumes a value between those bounds, x1 and x2. And this applies also to the other continuous probability distribution. But in this case, if you want to find that probability using the PDF for the normal, see that you take that as the parameter. This is constant. Then you have to integrate from x1 to x2, and this is the expression that you will have to integrate, which is an exponential, and this is, so you have x minus mu squared dx. The difficulty encountered is solving integrals for the normal density function necessitates or basically looks for other ways to solve this integral. So for example, we can use the tabulation of the normal curve area for quick reference, as we did for the binomial and for the Poisson and so on. However, it will be hopeless task to attempt to set up separate tables for every value of mu and sigma. So let's say you want to tabulate these tables and you need to find out all the values that you can assume or use for this normal distribution. That would basically create a book of this size for the tabulated values. So there was some research done to basically find better ways to tabulate the information for the probabilities of the normal distribution. Again, the normal is used a lot in engineering. So we are able now to transform all the observations of any normal random variable x into a new set of observations of a normal random variable z. Okay, so notice that now I'm referring to a new random variable. It's not x, it's z. And the difference between x for the normal and z is that the z random variable for the normal will assume that we have a mean of 0 and a variance of 1 for the normal distribution. And this is using the transformation. So the transformation of the random variable is here. So basically what you're going to do is you're going to get your value for x and you're going to transform x to a new random variable z. And what you do to get that transformation is you subtract the mean and you divide by the standard deviation. Okay, so again, this is what we're trying to do. To find the probabilities using the normal, you need to integrate this. This will take you a lot of time. So what we're trying to do is to solve this easier using tables. But if you want to tabulate all the values for this, you need to use a table for each mean and for each standard deviation. And that would take a lot of time as well, and you're going to have to carry a book with a lot of pages or a big file in your computer. So what we're doing is, in order to find an easy way, we're going to use a transformation. So we only have to create one table. We're going to use only one table in which the mean is 0 and the variance is 1 for the normal. In order to take any normal distribution, you can take any normal distribution with any mean and any standard deviation, and you can transform that to a normal 0, 1 using this. Okay, so that will allow you to compute any probability using the normal by using this transformation and using the tables for this transformation. This is what we call the standard normal distribution. The standard normal distribution is the normal distribution with mean 0 and variance 1. You can take any normal distribution and you can transform it to a standard normal distribution with mean 0 and variance 1 using this transformation. And I'm going to show you how to do it. Just want you to keep that in mind because we're going to be using this a lot. And that's why we're going to do it, okay? This is what. We need that because it's going to make computations easier for us. And also, we're going to deal with a lot of probabilities here with the normal, different mean. So if you want to keep using the same table, we need to use this transformation. So whenever x is a value of x, the corresponding value of c is given by this. It's coming from the previous slide. Therefore, if x falls between the values x1 and x2, the random variable c will fall between the corresponding value c1. So you're basically using the value x1 to find the transformation for x1, and the value of x2 to find the transformation for x2. So correspondingly, you can go from here, which is the PDF of the normal, to here. So now you have a nicer looking integral, which is easier to solve, but you don't have to solve it because we're going to have tables to find those probabilities. Okay? So where C is seen to be a normal random variable with mean 0 and variance 1. Okay? So we go from the PDF of the normal to a standard normal distribution with mean 0 and standard deviation 1, or variance 1, sorry. Okay? So the distribution of a normal random variable with mean 0 and variance 1 is called the standard normal distribution. So using this figure, this is what we're doing. We're going from the normal to a standard normal. Values of x now correspond to C1. Values of x2 correspond to the values of Z2. So the area here, the shaded area here, corresponds to this area for the standard normal distribution. If you find this probability, you're finding this probability. Okay? Okay, so let me pass this table because this is what I'm talking about, is the tabulated values for the normal 0, 1. And this is also in your textbook. If you go to page 735, this is part of the appendix. And today I'm going to show you how to use this table. So it's a kind of continuous process. Let me know if we are missing anyone. Okay, so for the exam, you're going to have this table available. How many? 2? No? Okay. So, again, in the exam, I'm going to provide you the table. So the area under the normal curve, we are now reduced the required number of tables for the normal curve area to just 1, which is the one you have, and that of the standard normal distribution. And this is a piece of the table that I just passed. This is a table in your textbook, 8.3, table 8.3, which is basically indicates the area under the standard normal curve corresponding to B, Z, less than Z, right here. So for values of Z ranging from 3.49, negative 3.95 to 3.49, I'm sorry. So basically, the values that you're going to see in the table correspond to the area from the value of Z to the left. Okay, and that applies for all the values. So the table has Z here in this corner, So for example, if you want to find the probability of Z being less than 3.45, negative 3.45, you can go here, you find negative 3.4. So the probability of Z being less than negative 3.45 is 0.003. Okay? That's the type of information that you can get from this table. Okay, so we're going to use some examples to show you how to use this table. Okay, so let's start with this one. Find the probability that Z is less than 1.74. So use the table to find out that probability. So you have two sheets or two tables basically. One corresponds to the negative values, the other one corresponds to the positive values. We're trying to find for 1.74. So if you go here, oh, it's not showing up. Okay, so let's try to use your table. So for 1.74, what would be the probability? 0.9591. That's what you found? Okay, correct. So go back here really quick. Okay, so remember that's the probability for Z. So coming back here, the probability of Z being less than 1.74 from the table equals 0.9591. And this is from table A3. Okay, now to find a Z value corresponding to a given probability, the process is reversed. So let's say we want to find the Z value leaving an area of 0.2148 under the curve. What would you do? Correct. You find that probability inside the table and then find the value of Z that corresponds to that probability. So in this case, you need to find the value of 0.2148. And that is negative 0.79, correct. So for that, Z equals negative 0.79. Were you able to find that number? Okay, so two things. You can find the probability for Z, and you can also find the value of Z from the table. Okay, so there's more practice here. So let's go a little bit, talk about this really quick. Okay, so here I have basically several important examples. Let's start by the first one. So the first one is asking what is the probability of Z greater than 1.26. So if you look at the figure, this is what this is asking for, this area. Right? Is that clear? What did you do to get that probability? Correct. You look at the complement. So the complement is 1 minus this area. Is that clear? So if you want to find that probability from the table, you need to look at the complement, 1 minus the probability of Z being less than or equal to 1.26. So you find this probability, and then find the 1 minus that probability, and you get the right probability. You have to be careful with this. And that's why I'm going through these examples. Because again, the table is giving you the area to the right. But in this case, I'm asking the area to the right. So if I'm asking the area to the right greater or equal, you need to look at the complement. The next one is very easy.
Good question.
Yes, sir.
I guess find probably a new less than 1.6. You just add 1 and then 0.26 you get it together. But there's no 1.26.
Yes, there's 1.26.
Oh, okay. That was,
Yeah, keep that going down, and you'll find 1.2, and then find 6 at the top. Okay. Any other questions? Okay. So for the next one, it's very easy, right? This is the information that the table gives you. So you just have to find this value, and that's 0.1949. Okay. The next one, this is using the property of the normal. So essentially, what I want to show you in this problem is that this probability to the right of negative 1.37 is the same probability of positive 1.37 to the left, because the graph is symmetric. But you can find this probability doing the same process that you did here by the complement, and you're going to find the same thing. So what I did was just look at the probability of the positive number, but again, if you follow this process, you're going to find the same probability. Is that clear? Okay. Let's look at this one. This is the probability for within this range, negative 1.25 and 0.37. So this is the area from negative 1.25 to 0.37. Again, the table is giving you the information to the left. So if you find 0.37, it is going to include everything to negative infinity. You need to subtract this area. And that's what we're doing. So we're going to find the probability of 0.37, and we're going to subtract the probability of minus 1.26. And that's going to give us this area. Okay? So this probability can be found by the difference of the two areas, this one and this one. And when you find those probabilities, for 0.37 is 0.64, for negative 1.25 is 0.10565. So when you look at the difference, the probability is 0.5386. Question. So this is very important. Remember, this is the area you want. This is the information you have from 0.37. You need to subtract this area. So you have to find the probability of minus 1.25 and subtract that from the area. Questions? Can I move to the next slide? No. Okay. We have two more examples, kind of similar to this one. Okay, so then move to the next one. The probability of minus 4.6. If you remember, one of the properties of the table is goes from negative 3.49 to 3.49. So here I'm asking you this probability. You look at the actual curve, that's outside the bound. So what would be the probability? The probability is going to be close to 0 or 0. Yeah. So 4.6 can be found exactly from the appendix. However, the last entry in the table can be used to find that probability, 0.0003. So that's basically 0. Okay? And the last one, this is what we did in the previous example. I'm giving you the probability, and I want you to find the value of z. So this is the area. So this expression can be written as the complement. And if you find the probability of 0.95, exactly the nearest value will be this one. So the corresponding value of z will be 1.65. Okay, one more thing before we go. And is the next problem, because I want you to connect what we're doing with the actual problem. Okay? So let's try to solve this problem. Given a random variable x having a normal distribution with mu equals 50 and standard deviation equals n, find the probability that x assumes a value between 45 and 62. So, what is the random variable here? X. Okay? So what would be the first thing you have to do if you want to use the standard normal distribution? You need to transform this x to z's. Okay? So that's the first thing you have to do. So z1 is 45 minus 50 divided by 10. So remember, this transformation is the following: x minus mu divided by the standard deviation. So this equals negative 0.5. Z2 equals 62 minus 50 divided by 10. So this is 1.2. Therefore, the probability of having x within 45 and 62 equals the probability of z between 0.5 and 1.2. Okay, so this is a transformation. We're going from one probability to the probability using the random variable z. So if you use the table now, c be less than 1.2 minus the probability of z be less than negative 0.5. This is going to be equal to 0.8849 minus 0.3085, and this is equal to 0.5764. Questions? If you know how to do these problems, probably you're going to have 30% of the exam, I would say 40% of the exam covered. Okay, so this is very important. Okay, I have your homeworks. So if you want to pick your homework from here, and I'll see you on Wednesday.